welcome to OneClass live stream. This is Chang, and today we're going to talk about some common math problems that were asked. So let's get started. Okay, so our first questions today is asking us what is an angle bisector in geometry. Okay, so let me So angle bisector in geometry is a line or a line segment that divides an angle in half. So let's draw it in another color. The black line here, we have an angle, and the blue line here is an angle is a line segment that separates these two angles by half. So the angle here is the same as the angle over here. These two angles are the same. Since these two angles are the same, this blue line is called a bisector. So the word bi means two in Latin, and sector means separate. So bisector would be something that separates something else in half. And in math, especially in the context of geometry, an angle bisector would be a line that separates an angle by half. So yeah, that's what's called an angle or bisector in geometry, or specifically an angle bisector. Let's do another example. So this is another angle, and we have another blue line right over here. Would this blue line be an angle bisector? The answer is no, because in this case, these two angles, they're not the same, so they're not spread equally. So this blue line would not be angle bisector because it doesn't separate the two angles in an equal half. It has to separate the angles in an equal half, and that's the definition of an angle bisector. Okay, and that concludes our first problem. And let's look at the sample solution over here on this side. So the angle solution, or the sample solution, not the angle solution. As the sample solution on this side, it just gives the definition of the angle bisector like we did. It's a line or a line segment or a ray that divides an angle into two congruent angles or two equal angles. Okay, so there are interior angle bisector and exterior angle bisector. This angle bisector, or this blue line over here, is an interior angle bisector because it divides an interior angle. Okay, and it also states the angle bisector theorem, but it's not directly related to angle bisector, so we didn't explain it in our solution. But over here, this solution is correct. So let's just say, great job, great job. The solution is correct. Okay, and let's move on to our next problem. Okay. So the next problem over here asks us how to write 7.5 as a fraction. So essentially, it's asking us to convert a decimal into a fraction. How do we do that? It is actually quite straightforward. So the first step of what we do is that we would try to separate this decimal into an integer part and a fractional part. So in this case, our 7.5 is equals to 7 plus 0.5 as a decimal. And 7 is just 7. 7 is an integer, but it's also a special kind of fraction because a fraction is a number that can be shown as two rational numbers divided by each other. And 7 can be shown as 7 over 1, which is a fraction. So an integer is a special type of fraction. And 0.5, since the 5 is on the 10th place, we would write the 5 on top, and it's on the 10th place, so we put the denominator as 10. So this, and we converted the number after the point into a fraction. And also 5 over 10 5 and 10 have a common factor, and their greatest common factor is 5. So we can divide 5 on both the top and the bottom of the fraction. And the top of the fraction is 5. 5 divided by 5 is 1. The bottom of the fraction is 10. 10 divided by 5 is 2. So here we have the fraction 5 over 10 is the equivalent of the fraction 1 over 2. These two fractions are equivalent in value. So right over here we have 7 plus 1 half, which is just equals to 7 and 1 half. Or if you want, we can convert it into 15 over 2. But writing it as 7 and a half is fine in most cases, or probably in all of the cases, because they're equivalent on value, unless your teacher specifically asks you for one of the representations. But these two, the representation in blue and the representation circled in green, these are equivalent representations. Okay, so this is our solution of converting 7.5 from a decimal to a fraction. Now let's look at the sample solution over there. Yep, they use a similar method. They just wrote 15 over 2, which is the same as 7 and a half, which are both correct. So let's just say correct solution. Excellent, excellent, excellent job. Yay. Cool. Let's look at our next problem over here. Okay, so our next problem is asking us to convert a fraction to a decimal. So for our previous problem, we converted a decimal to a fraction, and now we're doing the other way around, and we're converting a fraction to a decimal. So we're converting 3 over 8 to decimal. The easiest, there are a couple of ways of doing this. Obviously, you can use a calculator to do it, but the easiest way, I think, is probably long division. So how do we do long division? Is that 3 over 8, this fraction, is essentially 3 divided by 8. So we can just do 3 divided by 8 to find out what's this value of as a fraction. So right over here, we're doing 3 divided by 8. This is just a division sign. And obviously, you can just directly use a calculator to do it, but we're just going to do it by hand here to show you the complete long division process. So right over here, we have 3, and how many 8 makes a 3? We need to put a whole number over here, and we can't have a whole number multiplied by 8 makes 3. So the best we can do is a 0, and we know 0 times 8 is less than 3. So right over here we have 0. So let's just do 0 over here and 3 as a remainder. And next, we can drop a 0 over here. Notice that there's a point over here because this is a whole number, and in order to make our long conversion to be able to continue, we can add extra 0 over here. But obviously, we can't just write a 0 because that would make 30, which would change the value of our answers. So we put a dot over here, means this is 3.0, which has the same value as the number 3. All right, now we have the number 30. So we need to put a whole number as big as possible that multiplied by 8 is less than 30. So the best we can do is here is 3. 3 times 8 is 24, and the remainder of 30 minus 24, I should put a minus there as well, is 6. So we have 6 over here. And again, let's drop another 0 because we still have like a remainder. And we need to convert it to a decimal that's either like ends the long division or became a number that repeats itself. Sometimes And when you convert a fraction to a decimal, you know that the result is ended when this becomes a whole number. So for example, if the next is 60 and 60 minus 60 equals 0, that would end our process, and you would finish the process of converting a decimal to a fraction. Or when a number repeats itself, then that's also another way of when you know that you finished your process of converting a fraction to a decimal. Okay, let's continue. So what's the largest whole number that multiplies by 8 that makes the number less than 60? So the best thing we can do, let me think about it, it's 7. So we have 7 times 8, which is 56. And 60 minus 56 is equals to 40. And right over here, we would put a 5, because 5 times 8 is equals to 40. And 40 minus 40 is equals to 0. There, we have no remainders. And we have our answer, which is a decimal, and it's 0.375. So over here, we know that 3 over 8 is equals to 0.375 as a decimal. And this is our answer. This is our answer right over here. Perfect. So this is how we convert a fraction to a decimal. What we do is we just use long division. Very straightforward, isn't it? Okay, let's look at our sample solution over here. They didn't use long division. They are trying to see the power of 10 or 1,000, which is another way, and it also works. But you might get really large numbers in those cases. In this case, 1,000, it isn't that bad, but I think our ways of long division is better because it always works. Or I mean, this way always works as well because you're converting a fraction, but it might not be as straightforward to see that 1,000 divided by 8 is 125. If you don't have this memorized, it's less easy to see. Okay, so we have the same answer, and this solution is correct. I'll just say something like, long division might be easier. But that's also just a personal preference. Okay, so let's just say this solution is correct. Long division might be easier. Great job. Okay, now we can move on to our next question. So our question number 4 is asking, cool, what is the square root of 175? So it basically asks us to simplify the square root of 175. And the best way to do this is to use prime factorization. Okay, so the best way to do this is prime factorization. So what prime factorization is, it's that basically it converts a number into a lot of prime factors multiplied together. And that's what prime factorization is. So what is the prime factor of 175? The best we can get here is 5, because any integer ending in 0 or 5 has 5 as its factor. And 175 ends in 5, so 5 is one of the factors of 175. So we know that 5 is one of the factors. And what is 175 divided by 5? Just doing it quickly, we know that it's 35. So we know 175 is equal to 5 times 35. Now, is 35 prime? Obviously, 35 is not prime, because we just mentioned that any number that ends with 0 or 5, or any integer that ends with 0 or 5, has 5 as one of its factors. So we know that 35 also has 5 as one of its factors. I know that 5 times 7 equals 35. Now, is 7 prime? The answer is yes, 7 is a prime number because the only factor of 7 is 1 and 7, which is 1 in itself, so it's prime. So right here, we complete our prime factorization process, and now we can simplify this radical. So we just separate the radical sign. So this is the same in value as the previous expression over here. And we know that 5 times 5 is 5 squared. So we have 5 squared times root 7. And we know that 5 squared, which is 25, and the square root of 25 is just 5. Or similarly, we know that the square root sign is actually to the power of 1/2. Oh, whoopsie. The square root sign is actually to the power of 1/2. So we have 2 times 1/2, which is equal to 1, because the 2 cancels this out. The 2 cancels out with the other 2. So we have 5 to the power of 1, root 7. And 5 to the power of 1 is just 5. So our answer of the square root of 175 simplified is 5 root 7. Now, this completes our process of simplifying the radical square root of 175. Let's look at our sample solution over here. Our sample solution over here, exactly, they also use prime factorization, and they have 5 root 7. So our answer is the same, and the sample solution is correct, so it's our answer. So let's just say the solution is right. Well done, or well done. Yep. Now let's move on to our next problem, problem number 5. Okay, so this is another simplification problem, and it's asking us what is the square root of 192. So let's just do it here. What is the square root of 192? The square root of 192 is, oh, it's not written really well, 192. Okay, the square root of 192, again, we use prime factorization. Prime factorization. Okay, so we use prime factorization, and the most obvious prime factor of 192 is 2. Why? Because any integers ending with 0, 2, 4, 6, 8 has 2 as one of its factors. So we know 2 is a factor of 192. And in order to, and then we just find what's the integer that, so what's 182 divided by 2? So it's actually, it takes me a while, but it would be 96. Let me double check. 182 divided by 2. Yes, it is 196. Or sorry, it's 96. So 2 times 96 is 192. Now, obviously, as we said before, any integers ending with 0, 2, 4, 6, or 8 has 2 as its factor. So we know 96, 2 is also a factor of 96. And we know that 2 times 48 is 96. So right over here we have another layer of prime factors. And again, 48 has 2 as one of its factors. So we can do 2 times 2 times 2 times 24. Again, 24 ends with 4. This also has its 2 as one of its factors. So 2 times 2 times 2 times 2 times 12. Again, 12 ends with 2, so 2 is also a factor of 12. So I have 2 times 2 times 2 times 2 times 2 times 6. And again, 6 is not yet prime, but from here we can obviously see that 6 also ends with a 6. And 2 and 3 are both prime factors of 6. So we have another 2 times 3. And that finishes our prime factorization. Now we just need to simplify it even further. So let's count how many 2's there are. So there are 1, 2, 3, 4, 5, 6. There's 6 tools. So we have 2 to the power of 6 times the square root of 3. And also we know that 2 times the power of 6, the square root is the equivalent to the power of 1/2, and we have 2 to the power of 6 half right over here on the as well as the exponent, and 6 times 1/2 or 6 over 2 or 6/2 is just 3. So we have 2 to the power of 3 or 2 cubed over here, and we have 2 cubed root 3 on the other part. And 2 cubed is 3 2's multiplied together. Note that it's 3 2's multiplied together, so it's 2 times 2 times 2 instead of 2 times 3. Multiplication and exponentiation are different. So we know 2 times 2 times 2 is 8. So over here we have 8 root 3. Whew, that's a lot of work. Okay, so right here we know that the square root of 182 is the equivalent of 8 root 3. Let's look at our sample solution on the left side. So they also use prime factorization, and they arrive at the same answer as us. This is perfect. Let's just say the solution is correct. The solution is correct. Okay. Now we're at our 6th problem, and our 6th problem is asking us for the square root of 104. So let's write it down over here, our 6th problem, and it's asking us for the square root of 104. Square root of 104. Again, we use prime factorization. And we start by finding its prime factors. Again, any number that ends with 0, 2, 4, 6, or 8 has 2 as well as its factors. So we can just write 2 times 52 are 2 factors of 104. Again, 52 is also a multiple of 2, so we just write down 2 times 26 as 2 factors of 52. Next, we know that 26 again ends with 6. It's also a multiple of 2 or has 2 as its factors. So we know here that we have 2 times 2 times 2 times 13, and this completes the prime factorization of the square root of 104, because right here 13 is a prime factor, or 13 is prime, so that completes our process of prime factorization because all the factors over here of 104 are all prime. Perfect. Now, let's just simplify it. So the only 2 numbers that's the same, we need to take out all of the numbers that are all the pairs of numbers that are the same. We only have 2 2's that are the same here, so we just take out the 2 2's, and we have 2 times 13 on the other hand. So here we have 2 times 2, which is 4, and the square root of 4 is obviously just 2. So actually, let's write it incomplete. Let's just write it out. So 2 times 2 is 4. We have the square root of 4. And 2 times 13 is 26. We have 26. And the square root of 4 is just 2. So we have 2 root 26. And 2 root 26 is the square root of 104 simplified. Okay, let's write a sample solution here. Okay, sample solution here just directly factored out. So they basically just found out the answer by inspection, or in plain terms, they just found out the answer by looking at it, where we have a process of doing the prime factorization to find our answer. Cool. So the solution is correct, although it would probably be better if they put down the steps. So after you practice with prime factorization for a long time and you're familiar with it, you can probably just do it by looking at a number, and then you just know how to simplify it or finding the square root of it. But that takes a lot of practice. or at least some practice on your part. So maybe you are already at this level yet, you can just directly see the answer, or maybe you still need to do the process. Either way, the prime factorization always gives you the answer. Okay, so let's just say our solution here, that the solution is right. Yay! Okay, we're moving on to the next problem now. Our next problem asks us to convert 0.5 to a fraction. 0.5 is a decimal, and we're converting a decimal to a fraction. So again, 0.5, or I guess rather, let's do this over here so we don't confuse the point. So the 5 is on the 10th place, so it's on the first place after the top point here. So it's on the 10th place, so we know that 0.5, we can just take the 5, and we know it's the 10th place, so we can just write the 10 over here as a denominator, and that would be the equivalent of 0.5. Also, we could simplify it because the numerator 5 and the denominator 10 has a common factor of 5. That's their greatest common factor. So right here, we can just divide by both the top, the numerator, by 5, and divide the denominator by 5. And this would make this number, after dividing both the numerator and denominator by 5, would give you the same answer, because 5 over 5, or 5 divided by 5 is 1. 5 divided by 5 is 1. It's the same as 5 over 5. So the 5 over 10 here, we actually just divide this number by 1, which is equals to the number itself. So this would actually not change the value of 5 over 10, but rather it simplifies 5 over 10. Okay, so we're dividing the top by 5, and 5 over 5 is 1. We're dividing the bottom by 5, and 10 over 5 is 2. So our simplification here is 1/2, and 0.5 as a fraction, it's just 1/2. Cool, and that completes our solution over here. Let's just see their sample solution. I don't think the sample solution is correct, because right over here it says 0.5, meaning 0.5, and they actually did some funky stuff with percentage, and they arrived at the answer of 1/20, which is actually less than 1/2, which is not correct, because we're doing 0.5, not 0.05. 5% would be 0.05, and 0.5 would be 50%. Okay, so let's just say the solution here is actually not correct. The solution is incorrect. The solution is incorrect because 0.5 is 50%, while 0.05 is 5%. 0.5 or 0.5 as a fraction is actually 1/2, not 1/20. Alright, so let's just say the solution is incorrect. And let's move on to our next problem. Our next problem asks us to again convert a fraction to a decimal. So over here we're expressing 5/12 as a decimal. 5/12 as a decimal. So right over here, 5/12 as a decimal. Again, the easiest way to do this problem, or to do those kind of problem, is to use line division. division. Line division. Cool. So again, we are trying to divide. Again, 5 over 12 is the same as 5 divided by 12. And over here, we're just going to do the long division. Again, 0 times 12 is 0, and 5 minus 0 is 5. In order to maintain the value of 5, we just put a dot over here, so it's 5.00000, which is the same as 5. So over here, we have 5 again, and we just drop the 0 down. And the biggest number we can put here is actually 4. And 12 times 4 will be 48. 48. Perfect. And this is and the remainder of 15 minus 48 will be 20. And the largest number we can put here is 1. So that will just make 1 times 12 equals to 12. And 20 minus 12 will just be 8. Again, we drop the 0 over here. The 0 goes down. We drop the 0 down to here. And we need to try. So now we can't directly see what our biggest number would be. So let's just try some numbers out. First, let's try 7. 2 times 7 is 14. So we write the 1 here and write the 4 over here. And 1 times 7 is 7. But we need to add the 1, so it's 84. This number is larger than 80, so 7 is too big. Now, let's try 6. You know what? Let's do 5. Let's do 5. I'm just going to illustrate you something. So we have 80, 2 times, and we have 12 times 5, 12 times 5, 2 times 5 is 10, 1 times 5 is 5, and that would give us 60. So 80 minus 60, we can just, you would think that we just do here, and we would have a remainder of 20. However, the remainder is larger than the 12 over here. That means that we can actually do 6 instead of 5, because another 12 can fit inside of the 80. And the remainder we need to have must always be less than the divisor 12 over here. So the remainder we have over here for any of the divisions must be less than the number over here. Okay, so we know 7 is actually too big. So our 5 is too. We know 7 is too big and 5 is too small. So we know the answer is 6. So we have 12 times 6 over here, and 2 times 6 is 12. 1 times 6 is 6, but we have plus the 1 here, so it's 7. And the remainder is 8 again. So we have 80 again. And what number should we put here? It's actually 6 again, and it's just 72. And again, we have the remainder 8. So you would drop. Again, we have the remainder 8. So again, you would drop the 0 and put the 6 up here, and this goes on forever and ever. So what we do here is that we know that the decimal that we're converting this number to is actually goes on forever. So in this case, we just put a horizontal line on top of the number that's repeating. In this case, the 6 is a number that's repeating. So we just write our answer at 0.416 with a horizontal line on top of the 6, symbolizing that the 6 kept repeating infinitely. So over here, the decimal 5 over 12 is equal to the fraction 5 over 12 is equal to the decimal 0.416, where the 6 repeats infinitely or indefinitely. Okay, so this is our solution for this problem. Let's look at the sample solution they provided. The sample solution over here, they also use the long division method because that would be the most straightforward method. And yes, they also had the 0.416 repeating, or like the 6 is non-terminating. They could have just put the 6 on the first 6 over here, but I guess putting it on the other 6 is also okay. It's also correct, but it's not the convention, because conventionally we just put the bar on top of the 6. Because if you put the bar on 6 as a sample solution, it also symbolizes a repeating 6. That means just the 6 would repeat non-terminatingly. So it would just go 6, 6, 6. But if you just put the bar on the 6 in front of on the third number, on the 6 in front, it also means 6 repeating indefinitely. So this would be the same, but you can write one number less, which would be better because mathematicians are lazy as us. Or humans are lazy, I should say. Okay, let's say the solution is correct. The solution is correct. Great job. Great job. Moving on to our next problem. Here we have our next problem, and it's asked us to evaluate the cosine of 120 degrees. So that is a trigonometric problem, or trigonometry problem, or people just say a trig problem. Okay, let's do the cosine of 120 degrees. First of all, let's draw the angle on the unit circle. So here we have our unit circle, and the unit circle starts from here, and right over here we have 90 degrees, but 120 degrees is larger than 90 degrees, so we have a little more over here. That is 120 degrees, and that would be our angle over here, that 120 degrees angle. Or I guess I should probably do it in another color. You know what, let's just do it in another color, so it's more clear. So this is 120 degrees, and our angle, this would be our 120 degree angle. Cool. And we know that on the unit circle, the x values the cosine values are the x coordinates, and the sine values are the y coordinates. Over here, we know the horizontal axis is the x-axis, and the vertical axis is the y-axis. And we know that x is positive on over here on the positive side, or on the red side of the y-axis, and x is negative on this side. And since the angle, or the point over here, is on this side of the axis, and the cosine is the same as the x values on the unit circle, we know that cosine is negative. So just a note here, note that cos of 120, it's negative. We also know that the angle that we need to use is 30 degrees, because right over here, this angle is on the second quadrant. This is the first quadrant, second quadrant, third quadrant, and fourth quadrant. I know it goes this way instead of like the normal way that we usually do it, but that's just how math works. So this is the second quadrant, and you know for the second quadrant, our reference angle is 180 degrees minus theta, and the theta we want to know is over here. We know that the theta we want to know is 120, so we have 180 degrees minus 120 degrees equals to 60 degrees. And we know that 60 degrees is our reference angle. Also, the blue line should probably be more over here instead of over here. But it's okay. Okay, so reference angle is 60. Now, we just need to use the special triangle to find the exact value. We have two special triangles. The one we need to use here is the one that has the angle 60, which is this angle, or the triangle we need to use here is the triangle that has the value 60, which is this triangle over here. And the angle here is the 60 degrees angle. The angle there is the 30 degrees angle. I'll just label it for your sake, but we don't need this angle for this problem. Again, we are trying to get the cosine, or the cos of 60, this cos of 60, and the cosine is equals to adjacent over hypotenuse. So the adjacent of the 60 angle over here is 1, and the hypotenuse of the 60 triangle here is 2. So we have 1 over 2, and that is the cosine of 60. However, the question didn't ask for the cosine of 60. The question asked for the cosine of 120. And we know that based on our result over here, that the cos of 120 is negative based on our unit circle. So we know that the cosine of, or the cos of 160, the cosine of 160, or sorry, the cos of 120, or the cosine of 120 is negative. So the cosine of 120 is negative 1 over 2. Negative 1 over 2. And that completes our solution of finding the cosine of 120. Now let's check out the sample solution given. The sample solution given. The sample solution here, again, they also try to find the reference angle. They also write at the answer that the reference angle is 60 degrees. And yes, again, the cosine function is negative in the second quadrant, so we have the negative 1/1/2. It's the cosine of 120. It might be a little confusing here that they did cosine of 60 equals 1/2 equals negative 1/2, but they just meant that the cosine of 120 is negative 1/2. Or at least I suppose that's what they meant. Okay, so let's say the solution is correct, although it can be formatted better, but it's correct. Let's just say the solution is correct. Okay, let's move on to our next problem. Okay, for our next problem, we want to convert 0.875 to fraction. I'll just zoom in a little. And here, for our problem number 10, we want to convert 0.875 to fraction. We know that this is the 10th place, the first is the 10th place, the 7th is on the 100th place, and the 5 is on the 1,000th place. 1,000th place. So in this case, we just need to take the entire number, the entire 875, the entire number, and divide it by 1,000. That's how we convert this decimal to a fraction. So you have 875 divided by 1,000, which is the equivalent of 0.875, because the smallest number in this fraction is the 5, and 5 is on the 1,000th place. So we just take the entire number that's to the right of the dot and divide it by 1,000, because 5 is on the 1,000th place of the fraction of the decimal, and 5 is the smallest place. It's on the smallest place of this decimal. That's how we do those problems. We can leave our answer like that, but usually we want to simplify the fraction. So right over here, we want to simplify 575 over 1,000. We want to simplify this fraction, or reduce this fraction into its simplest forms. Now, how do we reduce fractions or simplify fractions? We just we just find the common factor of the numerator, the top number, and the denominator, the bottom number. What's the common factor of the top number and the bottom number? The most obvious one would be 5, but they are also another number that's also a common factor of between 875 and 1000 is 25. So you can just divide both the top number by 25 and the bottom number by 25. You can also just do 5, but after you do 5, you will be like, oh, we gotta do 5 again. So we can just directly do 25. So 1000 over 25, which is just 40, and 875 over 25, let's do long division over here, just to make sure our answer is correct. So 875 over 5, we know that 87 over 25 is 3, and that would make 75. 75. Whoopsie. 75. And our remainder would be 12. And we drop the 5. Whoopsie. And we drop the 5 would make our number 125. So what number times 25 equals 125? That would be 5. So 5 times 25 equals 125. Whoopsie. 125. And 125 minus 125 would equals to 0. And that completes our long division. Equals to 0. So here we have 35, and our fraction is reduced to 35 over 40, which can be further reduced because they have another common factor, which is 5. So you just divide both the top number and the bottom number by 5. And 35 divided by 5 is 7. 40 divided by 5 is 8. And here, now let's look at the numerator and denominator again. They only have one common factor, which is 1, and that's the best we can do. So this fraction now is completely reduced to its simplest form, and our final answer is that 0.875 converted to a fraction is equals to 7 over 8, or 7/8. Perfect. So that's our solution for this problem. Now, let's view the sample solution to see what they have. Yep, they had very similar solution as us, except they directly divided by two numbers by 125. But if you can't see 125 as their factor, you can just do 25 and then 5 like we did. And if you're having even more trouble than that, you can just divide by 5, and divide by 5 again, and you'll arrive to the same answer. Just make sure that for your final answer, you check that the greatest common factor of the numerator, the top number, and the denominator, the bottom number, is 1. That way you can be sure that your fraction is not just in a simplified form, but in the most simplified form. Alright, so that concludes our problem, and let's just give them a comment. Let's say, great job, the solution is correct. Solution is correct. Okay, now let's just move on to our next problem, or I guess let's go to our next problem. Our next problem asks us, how do we find the exact value of sine 45? You want to find the value of sine 45, we just use the special triangle we have, because the sine of 45 is a really common value. So we just use our special triangle over here. And our special triangle has a hypotenuse of √2 and the sides of 1, and the angle of this special triangle is both 45 degrees, because this is an isosceles triangle because two of its sides have the same length. Cool, so this is our special triangle. In order to find sine 45, we just pick an angle, which is 45 degrees, And we know that sine of a function is opposite over hypotenuse. So let's just write equals OPP, opposite over hypotenuse. Then the sine opposite to the angle 45 is 1. So we have 1 as the opposite side. And hypotenuse is root 2, so I have root 2 as the hypotenuse. And the value, or the exact value of sine of 45 is just equals to 1 over root 2. As for our sample solution here, you might get a little confused of why they said root 2 over 2 instead of 1 over root 2. Actually, they have the same value, but root 2 over 2 is more simplified than 1 over root 2, because the mathematical convention is that they don't like radicals on the denominator. So they don't want something with the square root on the denominator, but they're okay with square roots being on the numerator. So people just sometimes convert fractions in this form into the fraction in the form that's shown in the sample solution. You know what? We can quickly do it here. So to show you that they're the same value. So what they did is that they would multiply both the numerator and the denominator by root 2 in this case. Also, we know that root 2 divided by root 2 is just 1, because a number divided by itself is just 1. So over here, we have the numerator as 1 times root 2, which is root 2, and the denominator is root 2 times root 2, which is just 2. So we know that 1 over root 2 is the same value as root 2 over 2. So right over here, the sample solution actually has the same value as us. Okay, so that's how we find the exact value of sine 45. And let's just say, great job. The solution is correct. The solution is correct. Perfect. Let's move on to our next problem. Okay, our next problem here is asking us how do we simplify fractions with square roots. And the explanation is that basically there are 3 types of fraction with square roots in there, or 3 main types of fraction with square roots in there. The first type is the type that we just see above, where the square root is on the bottom of the fraction. The second type is the type that we see that later, where the square root is on the top of the fraction. Or the second type is the type where the square root is on the top of the fraction. And the third type is the type where the square root is both on the bottom and the top of the fraction. So we have something like so. For the first type and the second type, for the first type and the third type, we will need to do simplifications. Because again, like I mentioned previously, people or mathematicians are just in convention. They don't want the radical sign or the square root sign to be on the bottom of the fraction. But they like the square root sign or the fraction sign, or they like the square root sign or the radical sign to be on the top of the fraction. So this is, the middle one is great because the square root or the radical is on the top of the fraction, so no more simplification is needed. But for the first and the third case, we need to do more simplification. So how do we do the simplification? Well, again, we just multiply. For example, if I want to simplify, let's do simplification of root 2 over root 3. We just want to multiply this fraction by 1. And exactly what form of 1? We want to multiply this fraction by the so this fraction has the denominator of root 3. We just want to multiply this entire fraction by root 3 over root 3. So basically multiply the entire fraction by the bottom number. That way we multiply this fraction by 1 and we can cancel out the bottom denominator and making it not a radical. So on the top we have root 2 times root 3, which is just root 6. And on the bottom we have root 3 times root 3, which is 3. So over here, our result, we have a fraction, but here we have the radical sign or the square root sign is on the top of the fraction as the numerator. So this is simplified, and this is now at its simplest form. So this is how we simplify the fractions with square roots. First, identify which case is the problem. If it's the middle one, it's already at its simplest form, and you don't need to do more simplification. If it's the left one or the right one, then you need to do more simplification to move the square root from the bottom of the fraction to the top of the fraction, like we just did in this example. Okay, so this is how we simplify fractions with square roots. Now, let's look at the explanation given in the sample solution. Again, they did a similar example as us. They also did another example like this. So this is actually another case, but so you just multiply this so in the case where you have two numbers, one of them is an integer, the other one is a radical, you just multiply it by its reciprocal. So basically you just change the sign and then multiply this by also by 1, but the top and the bottom is both the reciprocal of the denominator of the original fraction. Okay, let's just say something like, great job, the solution is correct. Cool. Now let's move on to our next problem. Our next problem asks us to convert 0.875 as a fraction. So 0.875 as a fraction. So again, we need to try to see this, the number 8 is on the 10th place, the number 7 is on the 100th place, and the number 5 is on the 1000th place. Again, the 1000th place is the smallest number, or the smallest number, or the smallest place of this decimal. So we just need to put the 1000 as the denominator, because again, 1000 is the largest or the largest number out of 10, 100, and 1000, but it's the smallest place because it's the 1000th place of the decimal. So next we just need to write the entire right side of the fraction, and we put it, or the entire right side of the decimal, and we put it as the numerator of the fraction, as we have right over here. So now we just need to find the greatest common factor of both the numerator and the denominator to simplify this fraction even further. In this case, the greatest common factor of 875 and 1000 is 125. So 1000, let's just we divide both the top by 125 and the bottom by 125. 1000 over 125 is just 8. And 875 over 125 is, let me think about it, I think it's 7. Let me just double check quickly and do some mental math. Yes, it is 7. Perfect. So now we have our decimal converted into a fraction, and the fraction is also in its simplest form because the greatest common factor of the numerator and the denominator of the fraction is 1. So as in the greatest common factor of 7 and 8 is 1, so which symbolizes that the fraction is in its simplest form. So let's just say 0.875. 0.875 is equal to 70/8, which is a fraction in its simplest form. Perfect. So this is our solution. And let's look at the sample solution over here. Perfect. The sample solution over here is correct. So is our solution. Let's just say something like, great job. Actually, I just realized something. I'm just going to change the settings. Cool. So let's just say, great job. The solution is correct. Perfect. Okay. I'm having a little, I think my battery is almost out. I'm just going to quickly plug it in. Takes me 2 seconds. Okay. Perfect. Now, our next problem over here is asking us what is 4 to the 5th power. So our 14th problem over here is asking us what is number 4 to the 5th power. So it's asking us what is 4 to the power of 5. So in mathematics, a number to the 5 to this is called an exponent. So this means that there are 5 fours multiplied together. So 4 times 4 to the power of 5 is 4 times 4 times 4 times 4 times 4. So there are 5 fours multiplied together. So there are 1, 2, 3, 4, 5. There are 5 fours multiplied together. In this case, we just need to do the calculation over here. 4 times 4 is 16, times 4 is 64, and 64 times 4 times 4 is 64 times 16. And let's just do our math quickly over here. 64 times 16. 4 times 6 is 24. 6 times 6 is 36, which is 38. 384. And 1 times 4 is 4. 1 times 6 is 6. 384 plus 640 is equals to 1024. 1024. So 4 to the power of 6 is equal to 1024. 1024. Perfect. So let's just say our solution is correct. The sample solution also has it explained as 1024. So the solution is correct. Great job. I just need to note for one more thing. So basically, 4 times the power of 6, or 4 to the power of 6, it's not 4 times 5, because 4 times 5 is multiplication. 4 times 5 is multiplication, and 4 to the power of 5 is exponentiation. So 4 times 4 to the power of 5 is 4 times 4 times 4 times 4 times 4, which is this expression over here, but 4, which is 20. So yeah, they are very different. Please don't confuse them. Okay, and that concludes our explanation or our solution for 4 to the power of 5. And let's move on to our next problem. Okay, our next problem over here asks us what is 1.5 as a fraction. This is actually quite straightforward because let me just write it down over here. Oopsie. The mouse is moving oddly. It's just the internet. The connectivity is bad, probably. Okay, so let's get to our 15th problem. What is 1.5 as a fraction? 1.5 as a fraction. Oh, 1. 1.5 as a fraction. So we know that the 5 is on the 10th place. The 5 is on the 10th place. Oh, see. Oh, I'm trying. Our 5 is on the 10th place. Is on the 10th place. Oh, finally it works. The 5 is on the 10th place, and 1.5 is equals to 1 plus 0.5. These two fractions has the same value, and we know the 5 is on the 10th place, so the denominator is 10, and the numerator is just 5 because the numerator is what's on the right of the dot in the decimal. Okay, so now we have 1 plus 5 over 10, and we can further simplify the fraction 5 over 10 because 5 and 10 has a common factor, and their greatest common factor is 5. So we just divide both the top of the fraction by 5 and the bottom of the fraction by 5. So on the top, or the numerator, we have 5 divided by 5, which is 1. On the bottom, or on the denominator, we have 10 divided by 5, which is 2. So here we just have 1 plus 1 over 2, which is 1 and a half, which is also 3 over 2. Both the answer 1 and a half and 3 over 2 are acceptable because they're both fractions. It depends on which one you like better or which one your teacher requires if they had specific requirements. Alright, so that's how we convert the decimal 1.5 to a fraction. Now, let's look at our sample solution over here. Our sample solution is correct. Let's just say the solution is correct. I think the way that I weighted it is easier, but the solution is correct regardless. So let's just say the solution is correct. Good job. Yes. Okay, now let's move on to our next problem. I think it's asking us again what is an angle bisector. I think we already explained before that an angle bisector is a line or a line segment that divides the angle into two equal parts. So angle bisector is our question number 16, a angle bisector. Let me try to do text mode. An angle bisector is a line or a line segment or ray. I think the laptop stopped responding. Oh, perfect. Angle bisector is a line or a line segment or a ray. But I don't really like the word ray because I also do some physics. And I guess I think you can call it ray, but it just, I don't know why, but it just annoys me kind of. So I'll just call it a line or a line segment that divides an angle into two smaller equal angles. Or I guess just two equal angles is fine, because obviously if a line divides an angle into two parts, the two angles are going to be smaller. And let's just put it on the next line so that this stays on the same page. Cool. So this is what an angle bisector is. I'm just going to illustrate an example or a picture example so that you can see it more clearly. Okay, so say this is an angle bisector just divides this angle into two equal parts. Let me draw it again so it's better. Cool, now this part is more perfect. So basically, pretend this angle and that angle have the same value, or this line divides these two angles equally. I think it's pretty equal, at least from the naked eye, it's really equal. So in this case, this green line is just would be called an angle bisector, and that's what an angle bisector is. Okay, now let's look at the sample solution over here. Again, they had similar explanations, and they also stated some angle bisector theorem and equidistance theorem, which is quite obvious in my opinion, but you can look those up if you would like. I think the question only asked about angle bisectors. So yeah, that's what I explained. And let's just say great job. The extra information about the theorems can be really useful. So if you want, you can just look those up later on our OneClass OneClass site. But the information here are very useful. Okay, let's just say the solution is correct. And let's move on to our next problem. Okay, our next problem here asks us, what is the square root of 256? The square root of 256 is actually quite straightforward, because we know that the square root of 256 is just 16, because 256 is a perfect square, and the square root of 256 is just 16. However, let's pretend that you don't know that, and you're trying to find the square root of 256. How would you approach that kind of problem? If you're someone who doesn't have the square root of 256 memorized, which honestly is a lot of people, because just look at 256, how would you know that its square root is 16 or it's a perfect square without prior knowledge? Well, you can use something called a prime factorization to find out. What prime factorization is, it's basically it writes a number into a lot of factors, and all its factors are prime. So you just write the number in a way such that this number is a lot of other numbers multiplied together, and all of the smaller numbers that multiply together into this number, those small numbers are all prime, and they're all factors of this larger number. So yeah, this is how prime factorizations work. And we just take out the first prime factors of 256, and the first one we can see is probably 2, and the other factor of 256 that corresponds to 2 is just let me see, it is 128. Alright, so now we have 2 and 128. Again, 128 is also a multiple of 2, so we have 128. We can write it as 2 times 64, and again, 64 is also a factor of, also a multiple of 2, so we can take another 2 out, and that would be 2 times 32. Now we would have 3 2's, and let's just do 2 cubed times 32, which just means 3 2's multiplied together, so that we don't need to write all the 2's out. Again, 32 is also a factor of 2, so our 32 is also a multiple of 2, and 2 is a factor of 32. So we have another 2 over here, and we have 2 to the power of 4. Now we have 2 times 16 equals 32, so that's what we have here. And also, we know that 16 is actually just another 4 2's multiplied together. So we have 2 times 2 to the power of 4 times another 2 to the power of 4. So right now, we have 16 times 16, 2 times 4 times 2 times 4. So we have 8 2's multiplied together in total. So we have 2 to the power of 8. And right now, we know that the square root is actually the equivalent of to the power of 1/2. So we can write our 2 to the 8 like so. We can write our 2 to the 8 and just the same as before, and we can just convert the square root sign into exponents form, so we know it's actually times to the power of 1/2, so here on the exponents we have 8 times 1/2, or 8/2, or 8 over 2, or 8 divided by 2, which is 4. And now the square root of 256 is simplified to 2 to the power of 4, which is 2 times 2 times 2 times 2, which is 16. And here we know that the square root of 256 is 16, which is a perfect square. Perfect. So this is our solution. Again, there are 3 ways to find out. One is use prime factorization. The other is you just memorize the perfect squares. And the last way is obviously just use your calculator to find out. All right. So the sample solution just stated that the square root of 256 is 16, and they probably just memorized it because 256 is a perfect square. And they said that the square root can be positive 16 and negative 16. I guess we can also write it that way. Again, it depends on your schooling levels and in what context the question is asked. Both positive 16 and negative 16 are the square roots of 256. But usually writing 16 is fine, unless they specifically ask you for both, but some teachers want you to write both positive 16 and negative 16, so it depends. Make sure to read the questions carefully to know the specific requirements. Okay, the solution is correct. Let's just say great job. The solution is correct. Perfect. Let's move on to our next problem. Oh, I think we're actually a little over. Okay, so I guess we can end over here. Or actually, no, we're not over. Yes, no, we're not. We still have 10 minutes. Nice. We have 10 minutes together. Okay, so we can move to our next problem, our problem 18. Our problem 18, and our problem 18 asks us to find the exact value of the cosine of 570. 570. Okay, this is a trig problem. So how do we find the cosine of 570? To find the cosine of 570, we need to find the reference angle or the coterminal angle. So first, let's draw a unit circle. Unit circle is a little slow. Okay, let's draw a unit circle. Or I guess I'm not actually going to draw the actual circle, but just the reference frame. So we know we start the count from this axis over here, and we also know that if we go around a circle, or the angle of going around a circle is 360 degrees or 2 pi radians. So this is 360 degrees. So we know we went through the circle once, and 570 minus 360 degrees. Let's do 570 degrees minus 570 degrees minus 360 degrees equals to 210 degrees. So we know after that we went through a circle which is 360 degrees, we still need to keep going, and we just need to keep going for 210 degrees. We also know half a circle, or half of 360 degrees is 180 degrees. So we went, let's redraw the circle. So we went through the circle once. And we need to go through another half of the circle like so, and then so we need to go to another half circle. So let's do 210 minus 180, because 180 is half of circle, half of 360 degrees, and that would equal to 30 degrees. Cool, so we went through half a circle, and then we went for another 30 degrees. Let's just change our color to blue so that we can go for another 30 degrees. Okay, so we went another 30 degrees over here, and let's just draw the angle. Okay, so our actual angle actually went through 1.5 of a circle, and then stopped a little over here. This part is 30 degrees. Or I guess I should use another color for the 30 degrees. Let's use blue for the 570 degrees, because we just went 570 degrees all the way across like the area. So this is 470 degrees, or the angle. This is 470 degrees, and this small part is 30 degrees. All right, so our reference angle is actually just 30 degrees. So ref angle, let's use green. Oopsie. Our reference, cool. Our reference angle, it's 30 degrees. All right, and now we just need to find the actual value of cosine of 30 degrees. So let's see what's the value of cosine of 30 degrees. You know what, let's just redo it. Cosine of 30 degrees equals to question mark. Okay, in order to find the cosine of 30 degrees, again, we need our special triangle over here. This is our special triangle. We have two of them. This is one of them. They're very commonly used for trig problems. And the angle over here is 60 degrees, but it's irrelevant for this question because we're looking at the reference angle of 30 degrees, which is this angle over here. So now we know that cosine of an angle is adjacent over hypotenuse, and the adjacent side of this angle is the √3 angle. This is the adjacent side, and the hypotenuse of this angle of this triangle is 2, which is the hypotenuse. So we know that the cosine of 30 degrees is √3 over 2. However, what we really wanted to know is the cosine of 570 degrees instead of 30 degrees. So in order to find the cosine of 570 degrees, Again, we are in this quadrant. This is the first quadrant, this is the second quadrant, and we are at the third quadrant over here. In the third quadrant, the x values are negative on the unit circle, and again on the unit circle, the x values are the same as the cosine values. So since the x values on the unit circle on the third quadrant is negative, the cosine values on the third quadrant is also negative. So the cosine of 570 is actually negative. So the cosine of 70 is negative root 3 over 2. And that's our answer over here. Alright, now let's look at the sample solution that was given, and let's just briefly check through it. Yep, they also get the reference angle correctly, and they got the angle of cosine of 30 degrees, and yes, it's in the third quadrant. And yes, the cosine of 570 is negative root 3 over 2. Their solution is correct. So let's just say, great job. The solution is correct. Cool. Let's see what's our next problem. It's loading, loading, loading. Okay, our next problem is actually asking us what is root 20. This should be a really quick problem because it's quite straightforward. Again, we use prime factorization. And we're trying to find the, let's just write 20 again. You know what? Let's just use another part. Okay. Cool. So the biggest prime factor, so the biggest or the smallest or the first prime factor we can find for 20 is just 2. So we know 20 is 2 times 10. And again, 10 is 2 times 5. So we have 2 times 2 times 5. And that is the end of our prime factorization, because each number is a prime number, 2 is a prime number, and 5 is a prime number. So we have 20 is equal to 2 times 5, and we can separate the 2 because we have 2 2's, so we have a pair of 2's. So we separate the 2 and the 5, and 2 times 2 is 4, the square root of 4 is 2. So we have 2 root 5, 2 root 5 as our simplified radical. So we know root 20 is equal to 2 root 5 in this case. Alright, that's how we simplify the radical, and how we find out the square root of root 20, the square root of 20. Okay, so let's see the sample solution over here. Yes, they also used prime factorization, and they grouped the pairs of the same factor, just like we did, and we arrived at the same answer. So let's just say something like the answer or the solution, it's right. Excellent job. Cool. Let's just press the button that the solution is correct. Nice. So this is all we're going to cover for today. Thanks for coming to our live stream for OneClass. I hope to see you again in the future, and I hope you enjoyed our live stream today. If you really like our live stream, please click on the subscribe button down below. And this is OneClass. Thank you.